Okay, so hi everybody, welcome back. Today we're going to be starting a new chapter. That's chapter 16 of Giancoli. And the topic here is sound waves. So in the previous chapter, we learned about wave mechanics, and we developed different equations and diagrams that we can use to analyze the motion of a wave. What we're going to do here is apply all of those tools that we developed in the last chapter specifically to sound waves so we can learn more about sound. So let's start by talking about some of the basic characteristics of sound waves, and we'll start by just defining what we mean by sound in the first place. Okay, so at a basic level, sound is just another type of mechanical wave. So sound waves are a pattern of oscillations that travel through a material at some speed. And that material can be really anything. It can be solid, liquid, or gaseous. For example, sound waves can travel through a solid wall, which is why if your neighbors are being really loud, you can hear them in the apartment next to you through the wall. Sound waves can also travel through liquid materials. So sound waves can travel through water, for example. And also sound waves can travel through gaseous materials, like the air that surrounds us. So most of the time, when we talk about sound waves, we're going to be thinking about sound waves that travel through the air. And in that case, we're dealing with a longitudinal wave. So what I mean by this is the displacement of air molecules as the sound wave comes by is parallel to the direction that the sound wave is moving in. Okay, so in other words, air molecules are going to be vibrating back and forth in the same direction that the sound wave is moving in. That's what makes it a longitudinal wave. So let's take a look at an animation of a sound wave being produced so we can take a closer look at some of the properties of sound waves. So in this animation, we're going to have a piston here, which is going to create the sound wave by simply moving back and forth in this direction from left to right. And in doing so, it's going to push on the air molecules that it's directly in contact with, and then that is going to send out a sound wave which is moving to the right. So this animation is taken from this link, by the way. If you want to watch it again at home, you can click the link here in the lecture notes. But anyway, here's the animation. So if we take a look at any particular air molecule, let's say the one marked in red here, it's just moving back and forth from left to right. So it's oscillating horizontally. Now, if we think about which way the sound wave itself is moving, well, it's clearly moving to the right. So because the oscillations of the air molecules are horizontal and the wave is propagating in the horizontal direction, that's what makes it a longitudinal wave. Okay, so what we eventually want to build up to is a description, a mathematical description of a sound wave. And one way we could do this, one way we could describe the sound wave is in terms of the displacement of the molecules from their equilibrium positions. So again, if we take a look at this molecule shown in red, it has an equilibrium position right in the middle of its motion, and it's just oscillating around that equilibrium position back and forth. So if I had some kind of function that described the displacement of that molecule and all the other molecules in the air, then I would have a description of the sound wave. But also notice that in certain parts of the sound wave, the air is compressed and it's more dense and it has a higher pressure than the rest of the air. And in other parts of the sound wave, the air is expanded, it's less dense, it has a lower pressure than other parts of the air. So in other words, what's happening is we have these changes in air pressure from some equilibrium levels. So sometimes the air is at a higher pressure, sometimes it's at a lower pressure. So we can describe the sound wave in terms of those changes in pressure due to the expansion and compression of the gas. So in terms of displacement or in terms of changes in pressure, those are two different ways that we can describe a sound wave, and we'll get into both of those two descriptions. So how do we create a sound wave in the first place? Well, it's pretty simple. Any vibrating object is going to send out a sound wave into the surrounding air. So that vibrating object can be your vocal cords. That can send out a sound wave into the air. It can be the diaphragm of a speaker. It can be a tuning fork. All of these are just different examples of an object that's vibrating and in contact with air molecules and sending out a sound wave into the air as a result of that. So let's take the example of a speaker. Okay, so what happens in a speaker is we have what's called the diaphragm. This is some kind of surface that oscillates back and forth at some frequency, and it's in contact with air molecules, and it will push on those air molecules, causing them to oscillate, in turn sending out a sound wave that moves into the surrounding air, and that's why we can hear the sound created by the speaker. So again, I just want to remind you of something that we learned back in chapter 15. Mechanical waves do not transport matter. So if we take a look at the example of the speaker is not sending air molecules from here out into your ear, okay? All that's happening to the air molecules is they're vibrating back and forth around an equilibrium position. So the air molecules are not moving large distances. They're just oscillating around some equilibrium position. But what is traveling outwards is that pattern of oscillations and the energy that's carried by the sound waves. So the point is, mechanical waves transport energy, not matter. And so air molecules are not traveling large distances, they're just oscillating back and forth. And by the way, if we did have air moving large distances, you would call that wind, not sound, right? So sound is a different sort of phenomenon. Okay, so one really interesting aspect of sound is the fact that we can perceive it. So not only can we describe sound as a mechanical wave that moves through the air, there's a whole bunch of mathematical equations that describe how that wave works, but we can also have a sensation of sound. When you listen to music, it feels like something. So we want to get some understanding as to how that works. So let's say you're listening to music on a stereo system. So you're going to have speakers in the stereo system that are vibrating back and forth and sending out a sound wave into the surrounding air. Now, what happens when that sound wave enters your ear? Well, the sound wave is going to enter through a cavity in your ear, and it's going to move all the way until it reaches the end of that cavity where we have the eardrum. This is the eardrum, also called the tympanic membrane. So you're going to have air molecules vibrating back and forth, colliding with the eardrum at the end of the cavity, and those molecules will be exerting a force on the eardrum, which causes it to actually vibrate back and forth also. Now, the frequency of the incoming sound wave is going to be exactly the same as the frequency of the vibrations of the eardrum. So, for example, if the sound wave that comes in has a frequency of 200 hertz, then the eardrum is going to vibrate back and forth at a frequency of 200 hertz. And by the way, the frequency of the sound is what we perceive as being high-pitched or low-pitched. So high frequencies sound high-pitched to us, low frequencies sound low-pitched to us. And in a similar way, how loud the sound is has to do with the amplitude of those vibrations. So if your eardrum is vibrating back and forth with a very small amplitude, that's a quiet sound. If your eardrum is vibrating back and forth with a very large amplitude, that's a very loud sound. Okay? So that's how the information contained in the sound wave is picked up by the eardrum. It can pick up the amplitude and the frequency of the sound wave. Now, once the eardrum starts vibrating, those vibrations can be converted to electrical signals, which are sent through nerves to your brain, okay? And your brain is where the processing of that information happens. And there's a whole lot we could say about what's going on inside the brain and how those electrical signals sent from the eardrum are converted into a feeling or a sensation of hearing a sound or listening to music. But to be honest, that's not really my area of expertise. That's more of a topic for a psychology class. So again, if you want to learn more about what's going on in the brain, to process sound information and to give us a sensation of hearing music or hearing a sound, that would be a topic for a psychology course. So I left a link to a short video on the human auditory system. So you can click the link on the slide here if you want to go into this topic in some more depth. But again, I just wanted to cover the basics of how we perceive sound. Okay, so going back to the physics side of things, let's talk about the speed of sound. So the speed of sound waves in air is actually not a constant. It's going to depend on the temperature and the pressure of the air. So it will slightly change depending on weather conditions, in fact. But at 20 degrees Celsius temperature and a pressure of 1 atmosphere, the speed of sound in air is 343 meters per second. So this is sort of a standard value, but again, it can go up or down from that standard value depending on the temperature and pressure of the air. So in general, we have an equation for the speed of sound in a material that I'm not going to derive in this lecture here, but I'm going to post the derivation to Canvas in case you want to see it, and also you can find this derivation in the textbook. Here, I just want to quote the result because it's kind of a long derivation. So the speed of sound in a material depends on two factors in general. It depends on how compressible the material is and how dense the material is. So really, it just depends on those two factors. So V is given by, the speed of sound is given by the square root of B divided by rho. Okay, so rho is the density of the material. That's something we're already familiar with. That's the mass per unit volume of the material. But B, capital B, is called the bulk modulus. And this is how we measure the compressibility of the material. So if B is really small, the material is very easy to compress. If B is very large, then the material is very hard to compress. That's what the bulk modulus is telling us. But if you haven't seen this before, let me define the bulk modulus for you. So again, bulk modulus given by capital B is a measure of how hard it is to compress a material. And it's defined by the following equation. So B, bulk modulus, is equal to minus delta P divided by delta V over V. So on top, we have an applied pressure, delta P. And on the bottom, what we have is a change in volume divided by the original volume. That's what you should think of when you see delta V over V. So delta V is the change in volume you get, and V is the original volume that you had. So the picture you should have in your mind when it comes to bulk modulus is this. You've got some material here, and the original volume is V. So right now, there's some pressure, P, that's being exerted to that material. Now, let's say we increase the pressure, so we have P plus delta P, so more pressure than before. Intuitively, we know that this will cause the material to compress, so it's going to be a smaller volume than it was before. So the volume is now V plus delta V, where delta V is a change, and delta V is going to be negative because we've caused the material to shrink to a smaller volume, okay? Okay, so again, in the bulk modulus, on top we have delta P, which would be the increase in pressure we have. On the bottom, we have delta V, which is how much did the volume change as a result of increasing the pressure, divided by V, which was the original volume. Now, delta P is positive because we increased the pressure, but delta V is negative because we've decreased the volume. So to make the bulk modulus come out positive, we put the negative sign out front. That makes the bulk modulus come out to a positive value. Okay, so that's how the speed of sound works. It depends again on B, which I just defined for you, and rho, which is the density of the material. So let's do an example where we actually calculate the speed of sound in a material using this formula. So let's do the speed of sound in water using this formula. So the Mariana Trench is the deepest part of Earth's oceans, and it's nearly 11 kilometers in depth. At this depth, the pressure of the water is nearly 1,100 atmospheres, and the water is about 5% more dense than it is at sea level. So the pressure is crazy high at the bottom of the Mariana Trench, and the water is more dense as a result of that. So in other words, the water is compressed compared to water at sea level as a result of all that pressure. So based on this data, estimate the bulk modulus of water. So we're going to calculate B, the bulk modulus for water, using the definition. And then once we've done that, we're going to calculate the speed of sound in water from the bulk modulus and the density. And the density of water, by the way, is 10 to the third kilograms per cubic meter at sea level. So let's work this out. Okay, so if you think back to something that you learned back in Physics 45, you may remember that there is a depth and pressure relationship for a fluid like water. And again, this is a kind of an old concept from Physics 45 I'm calling back to. And it says delta P, a change in pressure, is given by rho times G times D, where rho is the volume, G is the acceleration due to gravity, and D is the depth within the fluid. So in this case, we're dealing with water, so 10 to the 3 kilograms per cubic meter, 9.8 meters per second squared for G. And then the depth, in this case, if we go all the way to the bottom of the Marianas Trench, is 11 times 10 to the 3 meters. That's the depth. So this works out to 1.078, if you just crunch the numbers, times 10 to the 8th power. Now, unit-wise, what we're dealing with is, okay, well, we have kilograms here and meters per second squared here. So a kilogram times a meter per second squared is a Newton. And then what we're left with is meters cubed on the bottom, and then a factor of meters on top, which would be meters squared on the bottom. By the way, that's a Pascal. That's the SI unit of pressure. If you were to convert this to atmospheres, you would get 1,100 atmospheres. So that's where that came from. So the pressure at the bottom of the Marianas Trench is about 1,100 atmospheres. So a tremendous amount of pressure. So let's think about what that looks like. So let's say we have, at sea level, a chunk of water here. Let's say it's mass M, okay? Now, if we take a look at the same amount of mass of water, but at the bottom of the Marianas Trench, it's going to be compressed to a smaller volume and a higher density. So that same mass of water is going to take up a smaller volume when it's under this much pressure. Okay, so remember that density is equal to mass over volume. And so that means symbolically we have rho is equal to m over v, which means the volume can be expressed as mass over density. So remember, in the bulk modulus formula, we have delta V divided by V. So what I want to do is figure out what is delta V divided by V for the water. So there's a change in volume again, smaller volume when you bring that mass of water to the bottom of the Marianas Trench. And So that's delta V on top. We can express that as M over rho, okay, minus M over rho naught. So here, let's call the density at sea level rho naught, and the density down here, rho. Okay, and then we're dividing that by V, which is M over rho naught. So you can simplify this quite a bit. If you multiply on the top and bottom by rho naught over M, you're going to get rho naught divided by rho minus 1. Okay, that's how you can simplify this. Okay, so again, what do we know? The density rho is 5% greater than rho naught. So the density at the bottom of the Marianas Trench is 5% greater than at sea level. And how can we turn that into equations? Well, rho is equal to rho naught, and then add 5% to that, add 0.05 rho naught to that, which is 1.05 times rho naught. So delta V over V is equal to, we've got rho naught divided by 1.05 rho naught, cancel those out, minus 1. So this is just a number, and it's going to come out to minus 0.0476. This is what we call the fractional change in volume. And you might have guessed that the volume would decrease by 5%, but it's not exactly that. You have to work it out. It's a little bit less than that. Okay, so next we can calculate the bulk modulus because we have minus delta P, we have the change in pressure, we know that, divided by delta V over V, the fractional change in volume. So we have minus 1.078 10 to the 8 pascals on top for delta P. And then we have minus 0.0476 for delta V over V, which works out to 2.265 10 to the 9 pascals. So that's the bulk modulus of water that we've estimated. And that's just an estimate based on some data we have about the Marianas Trench. It's pretty close to the actual value, but we've actually overestimated slightly. But we can use that to calculate the speed of sound because V is equal to the square root of B divided by rho. So we have the square root of, again, put in the bulk modulus, 2.265, 10 to the 9. And we're going to divide that by rho, which is 10 to the 3 kilograms per cubic meter. Okay, in terms of the units, I just want to show you something real quick. 1 Pascal, again, is 1 Newton per square meter, which is the same as 1 kilogram meter per second squared divided by a square meter, which is 1 kilogram over a meter times a second squared, if you simplify that. So in my calculation for V, I'm going to write 2.265 10 to the 9 pascals as 2.265 10 to the 9 kilograms divided by meters second squared like this, just so we can see how the units work out at the end of the day. Okay, so numerically, if you crunch those numbers, you're going to get 1,500. And unit-wise, kilograms will cancel. We're going to have in the square root, so meters canceling here, this becoming meters squared. But that meters squared will go to the top, and then we'll have seconds squared on the bottom. So that's about 1,500 meters per second. So that's what we've calculated for the sound speed in water. And that's pretty close to the actual value, which is 1,480 meters per second. So we did a pretty good job of estimating the speed of sound. Okay, so next, let's talk about how to mathematically represent a sound wave moving in one dimension. So what are some formulas that we can use to describe a sound wave? So one way we could do it is in terms of the displacement of air molecules, and that would be a function d of x and t. In fact, we know exactly how to do this already. We learned this back in chapter 15. The displacement of a wave as a function of position and time is given by a times sine kx minus or plus omega t. And technically we have a phase angle, but I'm just leaving that off for now. And how do we interpret the sign here? Well, it's going to be negative if our wave is moving in the plus x direction, and we're going to choose the positive sign if we're moving in the minus x direction. Also, remember that k is called the wave number. It's given by 2 pi over lambda. And omega is the angular frequency. It's 2 pi times f, where f is the frequency. Also, a is called the amplitude of the wave. Now, in this case, the amplitude represents the maximum displacement of the air molecules from their equilibrium position. So it tells you how much are the air molecules actually moving back and forth. So small amplitudes would be not moving that much. Large amplitudes means they're moving back and forth a lot more. Now, there's another way to do this. There's another way to represent the sound wave in one dimension, which is in terms of pressure changes. So what I'm going to do now is derive how we can express a sound wave in terms of pressure changes. Okay, so let's consider a sound wave that's moving in the positive x direction. So in terms of the displacement of the air molecules, we already know that this is given by d of x and t equals a times sine kx minus omega t. That negative sign, of course, indicates that we're moving in the positive x direction. Now we want to turn this description of the displacement of air molecules into a description of the pressure. So the way we're going to get a handle on that is to bring in the formula for bulk modulus, which is B equals minus delta P over delta V over V. And that can be rearranged to say that delta P is equal to minus B times delta V over V. Okay, so we're talking about a sound wave. So what do we even mean by a change in volume? What's delta V all about? Well, the idea is when a sound wave passes through, okay, the air will be compressed by some amount, or it can be expanded depending on exactly what we're talking about. Let's say the air is being compressed at this moment. And let's say it's compressed by some distance, which we'll call delta D. So in particular, let's think of a fluid element. So this is a little chunk of air. And its surface area, its cross-sectional area is S, I should say. And its length is, let's call it delta x. So the idea is when a sound wave passes through this fluid element, the fluid element is going to be compressed and stretched out and then compressed and then stretched out. Let's say this is the moment where it's being compressed. And again, we'll call that distance that it's compressed delta D, like this. So that's the picture you should have in your mind. So going back to the expression for delta P, we have minus B. Now delta V is the change in volume that results from the sound wave passing by. So that would just be the shaded region, which is S times delta D. And V would be the original volume, which would be S times delta X. So what we can do is cancel out S, and we're just left with delta D over delta X, which should kind of remind you of something. This kind of looks like a derivative, doesn't it? In fact, if we take the limit where delta X goes to 0, then this does become a derivative. This becomes delta P equals minus B times the derivative of D with respect to X. And we have to use partial derivatives here because, of course, there are two variables, X for position and T for time. And we're talking about the derivative with respect to X, not time. So this is going to be minus B times the derivative with respect to X of this function, the displacement, which again is A sine kx minus omega t. That's the derivative we have to take. Okay, so I have minus b out front. When I take the derivative of the sine function, I get cosine. So I have a and then cosine kx minus omega t, but I'm not done yet because I need to take the derivative of what's inside of the sine function, which brings out a factor of k. So I have minus b times a times k cosine kx minus omega t. That's the change in pressure. Okay, so I'm going to make a bunch of different substitutions now. The first one is this. V is equal to the square root of b divided by rho. That's the sound, the speed of sound. So if I square both sides, then I'll have v squared equals b divided by rho, or I could say b is equal to v squared times rho. Also, remember that k is equal to 2 pi divided by lambda, and v is equal to lambda times f. So that's the fundamental relationship between speed, wavelength, and frequency. So this tells us that 1 over lambda is equal to f divided by v. So k, therefore, is going to be 2 pi times 1 over lambda, which is f divided by v. So I'm going to make this substitution for b, and I'm going to make this substitution for k, and then we'll see what comes of that. So I have minus b, which is v squared times rho, times the amplitude a times k, which is 2 pi f over v, times cosine of kx minus omega t. And what do we have from all that? We have delta p is equal to minus. Overall, we have 2 pi. One factor of v cancels on the bottom. And then we have rho, we have v, and we have a, and we have f. And then cosine kx minus omega t. But all this stuff out front is just one big constant. And what it represents is the maximum value of delta p. So the maximum pressure change that will occur in this sound wave is equal to 2 pi times rho. That would be the density of the material, times v, the speed of the sound wave, times a, the amplitude, times f, the frequency. That is the maximum pressure change in the sound wave. So therefore, if we want to describe the sound wave in terms of pressure variations or changes in pressure, what we have is delta p as a function of x and t is equal to minus delta p max times cosine kx minus or plus omega t, where delta pm is called the pressure amplitude. Again, that's the maximum change in pressure relative to some equilibrium level. And the formula for delta P max is equal to 2 pi times rho times V times A times F, where again, we have 4 variables. Rho is the density of the air, V is the speed of sound, A is the amplitude, and F is the frequency. That's how we describe things now in terms of pressure. So one thing you should notice about the 2 functions that we've derived, one for displacement of air molecules and the other for pressure, is that they're out of phase with each other. And that means when one of them is at a maximum, the other one is at 0. So remember, displacement is given by a simple sine function, a sine kx minus or plus omega t. So let's plug in t equals 0 for the time and just look at the displacement as a function of x when time is equal to 0. And then on this axis, we'll just have x. So this is just a sine function, sine of kx. So that would start at 0, and then you'd have your usual sine curve. In terms of delta p, again, if we set the time equal to 0, then we're going to have minus some cosine of kx. So this is going to start at a negative value, then it will shoot up, and then the sine wave will just oscillate in the normal way. But the point is, they're not in phase. When the displacement is at 0, the pressure is at a maximum or a minimum. And then when the pressure is at 0, the displacement is at a maximum or a minimum. What we call that is being 90 degrees out of phase. That's something to remember when it comes to displacement and pressure. So again, let me just show you a few other points on the graph. Here we have a maximum in the displacement. If you follow that down to the pressure graph, that will be pressure delta P is equal to 0. Here we have a peak or a maximum in pressure. If you follow that to the displacement graph, displacement is equal to 0. So that's what it means for them to be 90 degrees out of phase. Okay, so let's use some of the formulas that we've developed in this chapter and the last one to make some calculations. So let's say you're having a normal conversation with someone who is standing a few feet away from you. In that case, the intensity of the sound waves that you're receiving is going to be somewhere around 3 times 10 to the minus 6 watts per square meter. So that's the intensity for a normal conversation. So let's say the frequency of the sound waves is 450 hertz. That's kind of typical of a speaking voice. What will the displacement amplitude A of the sound waves be? And then what will the pressure amplitude delta P be at the same time? So we need some other numbers to do the calculation. We need the speed of sound in air, which we'll take to be 343 meters per second. And we'll take the density of air to be 1.29 kilograms per cubic meter. So for the displacement, A, give that in meters. And for the pressure, delta P max, give that in pascals. I have 2 equations that I put at the bottom of the slide. One is for the intensity of a mechanical wave. We derived this guy back in chapter 15, so you might have to use that. And then the pressure amplitude, delta PM, which we just derived, you also will need to use this. So pause the video, see if you can make these calculations, and then we'll go through it together. Okay, so we'll start with the formula for intensity. I is equal to 2 pi squared times V times rho times F squared times A squared. Now what we can do with this is solve for A, the amplitude or the displacement amplitude of the wave. A squared is equal to I over 2 pi squared times V times rho times F squared. If we simply take the square root of both sides, then we'll solve for A. And here's what we'll have. Plugging in the numbers, the intensity is 3.0 10 to the minus 6. Then we have 2 pi squared on the bottom. V is 343 meters per second. Rho is 1.29 kilograms per cubic meter. And then finally F is 450 hertz. And remember, hertz is just the same as inverse seconds. And we square that. And then we square root the whole thing. But what about the units of intensity? Remember, this is given in watts per square meter. So let's just do a quick analysis of the units. Remember, a watt is a joule per second. So this is joules divided by seconds times meters squared. Also remember that a joule is a kilogram times a meter squared per second squared. And that's going to divide seconds and meters squared. So overall, meters squared cancel out. And then we have seconds cubed on the bottom. So intensity units can also be written as kilograms divided by seconds cubed. So I'll put that in the calculation here. And to see how the units work out, seconds cubed is going to cancel on the top and bottom. So we'll kilograms, and we'll just be left with a factor of meters at the end of the day when you take the square root. And this works out to 4.118 10 to the minus 8 meters, which actually we want to round that to 2 sig figs, which gives us 4.1 10 to the minus 8 meters. Now that is a tiny distance. That just goes to show you how sensitive our ears are. We can detect displacements of air molecules that are on the level of 4.1 times 10 to the minus 8 meters, and we have no problem hearing that sort of sound wave. So these are tiny little displacements that our ears are able to pick up on. Now, the next thing we can do is calculate the pressure amplitude, delta PM, which is given by 2 pi times rho times V times A times F. Now that we have A, we can do this calculation. So we have 2 pi, rho is 1.29 kilograms per cubic meter, V is 343 meters per second, A is 4.118, 10 to the minus 8 meters. And then F is 450 inverse seconds. That's the same as 450 hertz. Okay, this gives us 0.05152. And then we'll keep 2 sig figs on that. Unit-wise, we have kilograms on top. On the bottom, we're going to have a single factor of meters because we have meters here on top, and then meters cubed on the bottom. So overall, just a factor of, meters on the bottom. And then we have 2 factors of seconds, one from here on the bottom. So we have seconds squared also on the bottom. Now, I showed earlier that this is equivalent to a Pascal, so I'm not going to do that again. And when we round it, we get 0.052 pascals, which again is a tiny little change in pressure. Remember, 1 atmosphere of pressure is something like 10 to the 5 pascals. So this is less than 1 pascal, much, much less than 1 pascal. And we're able to detect that tiny little variation in pressure. Okay, so let's try to relate some of these mathematical ideas to how human hearing works. So the first thing to note is that what we perceive to be the pitch of a sound, that is whether it sounds high-pitched or low-pitched, has to do with the frequency of the sound wave. Now, a very low-frequency sound wave sounds like it has a lot of bass, it sounds very low-pitched, it sounds deep. A high-frequency sound wave sounds high-pitched, it sounds like it has a lot of treble in it, That's kind of the difference between high and low frequencies. And as humans, our ears can detect sound with frequencies in a certain range. We can't hear every single frequency. We can only hear sounds that are between 20 hertz on the low end and about 20 kilohertz on the high end. We can hear in that range, but not outside of it. Now, the next thing to note is that what we perceive as the loudness of a sound, how loud it sounds to us, corresponds to the intensity of the sound wave. So high intensity waves sound loud, and then low intensity waves sound quiet. So again, when it comes to intensity, there's a certain range that we can hear. The lowest intensity that we can actually pick up is about 10 to the minus 12 watts per square meter. That would be something you can barely hear, and anything below that would not be something you can detect. And then about 1 watt per square meter, that's where the sound is so loud that it starts to become painful. So the normal range of human hearing is about 10 to the minus 12 to about 1 watt per square meter. So it's a pretty big range of sound intensities. And for that reason, the way our hearing works is our perception of sound intensity is logarithmic, not linear. So what do I mean by this? If we have two different sounds, and let's say one of them is intensity 0.1 watts per square meter, and the other is 0.01 watts per square meter, you might think that one is 10 times louder than the other, but if you put a human to the test and you ask them, how much louder does this one sound compared to this one, on average, they're going to say it's about twice as loud. So in other words, we perceive something that is actually 10 times more intense as being twice as loud. That's just how our brain processes the difference, basically, in a logarithmic way. So to better reflect the way we perceive sound, rather than talking about sound intensity, we have something called sound level, which is measured in decibels. Okay, it's a logarithmic scale for sound intensity, and it's measured in decibels. So the sound level given by beta is equal to 10 times log base 10 of I divided by I naught. That's how you calculate the sound level in decibels. So I is going to be the sound intensity that you're dealing with, and I naught is going to be a reference value for that intensity, which is equal to 10 to the minus 12 watts per square meter. So if you want to calculate how many decibels a sound has, you plug in the intensity, you divide by this reference value, you take the log of that, and then you multiply by 10. That's how you get the sound level in decibels. Okay, so what we have here is a table with various sounds, and on the middle column we have the sound level in decibels, and in the rightmost column we have the intensity measured in watts per square meter. So the sounds go from very loud to quiet as we go down the table. So if you're standing 30 meters away from a jet engine, the sound level is 140 decibels, which is very loud, painful. It's going to damage your ears. That corresponds to a sound intensity of 100 watts per square meter. Now, if you're at a loud rock concert, the sound level is around 120 decibels typically, which is almost painful. That's about 1 watt per square meter. If you're hearing a fire engine blaring a siren at 30 meters away, that's going to be about 100 decibels or 10 to the minus 2 watts per square meter. And there's some other values here, which I'm not going to go over, but the point is there's a relationship between the intensity and the sound level in each one of these cases given by the formula we just outlined. Beta is equal to 10 times the log base 10 of I over I naught. Okay, let's do a little bit of practice with the formula beta is equal to 10 times log base 10 of I divided by I naught. And let's do some of the calculations that are shown in the table. So remember, I naught is equal to 10 to the minus 12 watts per square meter. And one of the examples in the table was a painful sound. That would be I equals 1 watt per square meter. That's where the sound is so loud that it starts to become painful. And if we plug in that value into our formula for the sound level, beta is equal to 10 times log base 10 of 1 watt per square meter divided by 10 to the minus 12 watts per square meter, which we can cancel out the units. And then we have 10 times the log of base 10. 1 divided by 10 to the minus 12 is just 10 to the 12. And that 12 power can come out to the front. So we have 10 times 12 times log base 10 of 10. That right there is 1. If you take log base 10 of 10, you just get 1. So we're just left with 10 times 12, which is 120 decibels. Okay, so 120 decibels is where the sound begins to become painful. And then a barely audible sound would be I equals 10 to the minus 12 watts per square meter, which corresponds to beta, the sound level, equals 10 times log base 10 of 10 to the minus 12 watts per square meter over 10 to the minus 12 watts per square meter. So that's just 10 times the log base 10 of 1, right? Well, log base 10 of 1 is 0, so this would be 0 decibels. So this scale, the decibel scale, is designed so that 0 is the quietest sound that we can hear, just barely audible. And then anything above that is stuff we can hear. Anything negative should be inaudible to us. It's too quiet to hear. So the normal range of human hearing, which of course will depend on the person, some people have better hearing than others, but the normal range of human hearing is beta can be somewhere between 0 and 120 decibels. That's what we see. Okay, so here's an example for you to try out. Let's say we have a passenger airplane flying directly overhead about a mile above you. Typically, the sound level in that sort of situation is going to be about 95 decibels. So what is the corresponding sound intensity measured in watts per square meter? So try to figure this out, pause the video, see if you can make the calculation, and then we'll go through it together. Okay, so once again, we'll start off with beta is equal to 10 times the log base 10 of I divided by I naught. But this time, we would like to figure out what the sound intensity I is. So first, let's divide through by 10. So we have beta over 10 is equal to log base 10 of I divided by I naught. How can I get rid of the logarithm? Well, I can take 10 to the power of both sides. So now on the left side, I have 10 to the beta over 10 power, equaling I divided by I naught, because when you take 10 to the log base 10 of something, you undo the logarithm. And then we have I equals I naught times 10 to the beta over 10 power. Okay, so at this point, let's plug in what we know. I naught is equal to 10 to the minus 12 watts per square meter. And then we have 10 to the power of beta, which is 95, divided by 10. Now, what we're dealing with is 10 to the minus 12, multiplying 10 to the 9.5 power, because 95 over 10 is 9.5. And then this is watts per square meter. Now that's the same as just adding the two powers. So minus 12 plus 9.5. This is 10 to the minus 2.5 watts per square meter. And if you crunch those numbers, you're going to get 3.2, 10 to the minus 3 watts per square meter. So that's the sound intensity you're going to be hearing in this situation. Okay, so let's take a look at an example where we use these ideas of sound level and intensity once again. When you are standing 3.50 meters away from a loudspeaker, the sound level is 115 decibels. So the first question is, what is the power output of the speaker in watts? And then a follow-up to that is, how far would you have to stand from the speaker in order for the sound level to be reduced to 105 decibels? We're going to assume that the speaker is an isotropic source of sound waves, so that means it's radiating equally, it's radiating energy equally in all directions. And we're going to ignore any kind of complicating factors like sound waves reflecting off the walls in the room. So there are two things we'll keep in mind here. For an isotropic source of sound, we expect it to follow the inverse square law that we developed back in chapter 15, where I is equal to the power of the source divided by 4 pi r squared. We're going to use that. Then the sound level is given by beta is equal to 10 times log base 10 I over I naught. We're going to use both of these ideas in this problem. So let's get into it. Okay, so in the previous example we did, we saw that we could take this formula for the sound level, beta is equal to 10 times the log base 10 of I over I naught. And we can rearrange this, we can solve for I. And in doing so, we're going to get I is equal to I naught times 10 to the beta over 10 power. So we're just going to use that result from before. And when you're standing at a distance of r is equal to 3.5 meters, we're told that beta, the sound level, is equal to, 115 decibels. Yeah. Okay, so the corresponding sound intensity, I, is going to be I naught, 10 to the minus 12 watts per square meter, times 10 to the power of 115 over 10. And so we have 10 to the minus 12 times 10 to the 11.5. 115 over 10 is 11.5. And then we have watts per square meter. Okay, so we've got the minus 12 power. We've got the 11.5 power. We add those together to get minus 0.5 watts per square meter, 10 to the minus 0.5 watts per square meter, I should say. And this works out to 0.3162. We're going to keep 3 sig figs because the value of beta that went into this was to 3 sig figs. And then we have watts per square meter. Okay, so next we're going to use the inverse square law to relate this sound intensity, I, to the power of the speaker, P, because I is equal to P divided by 4 pi r squared. So P is equal to 4 pi r squared times I. So the power output of the speaker is 4 pi times 3.50 meters squared. Remember, that's the distance away from the speaker. That's the R value. And I is equal to 0.3162 watts per square meter. And okay, this works out to 48.68 watts because meters squared cancel out on this. And we'll round that to a nice 48.7 watts. So that's the power output of the speaker. Remember, a watt is a joule per second. So this is saying every second that passes by, the speaker outputs sound energy equal to 48.7 joules. Okay? Okay, to answer the follow-up question then, we want to know, so here's the follow-up. what is R? So what is the distance from the speaker when the sound level is equal to 105 decibels? Okay, so one thing we can immediately do is say that I is equal to I naught times 10 to the beta over 10 power to calculate the sound intensity that we're talking about, which again is I naught 10 to the minus 12 watts per square meter times 10 to the power of 105 over 10. So we have 10 to the minus 12 times 10 to the 10.5 power. And then we have watts per square meter. And what we get is 10 to the minus 1.5 power watts per square meter, which will give you 0.03162 watts per square meter. So that's the sound intensity I that we're talking about. And then using the inverse square law, the next thing we can do is relate that sound intensity to the distance. I is equal to P divided by 4 pi r squared. So if we solve for r squared, that's going to be P divided by 4 pi times I. And of course, we'll have to square root that to get R. Okay, remember, P is the power output of the source, which is 48.68. And that will be measured in watts, divided by 4 times pi, times the intensity I, which is 0.03612 watts per square meter. And if you take a look at the units, this will work out to meters. And you'll get 11.057, which we want to round to 3 sig figs, or 11.1 meters. So that's how far away you have to stand in order to be hearing a sound that's 105 decibels. So that brings us to the idea of a standing sound wave. So remember back in chapter 15, when we first encountered the idea of a standing wave, it turns out all of that can be applied to sound waves as well. So what does this look like? So in chapter 15, we considered a string that's held down at both ends, and we saw that that's the type of thing that can support a standing wave because the string being held down at both ends confines the wave between those two endpoints, so it can't move outside of those two endpoints. So you get a standing wave that's actually not moving in any particular direction. It's just confined to the string itself. Now, a standing wave, as we saw, can be thought of as a superposition of two waves that have equal frequency and equal amplitude, but are traveling in opposite directions. So in other words, you have two waves that are exactly the same. The only difference is they're traveling in opposite directions. If you add those two waves together, what you get is a standing wave. So that's just sort of a recap of what we saw in chapter 15. So in a similar way, you can get a standing sound wave if you have an enclosed space that's filled with air. So let me give you a few examples of this. We have a seashell. Okay, that's an enclosed space that's filled with air. So you can get a wave that is just confined to that enclosed space. That would be a standing sound wave. And if you've ever put your ear up to a seashell, it kind of sounds like the ocean. It kind of seems like the seashell is making some kind of noise. And the only reason for that is you have a standing sound wave inside of that confined space. A lot of musical instruments also take advantage of this fact. If you have any kind of wind instrument like a trumpet, inside of that enclosed space of the trumpet, you can create a standing sound wave. Also, even in an acoustic guitar, there is a cavity inside of the acoustic guitar, which again is just some kind of enclosed space filled with air. You can get a standing sound wave in there as well. Okay, So let's start by thinking about a one-dimensional standing sound wave. It gets a lot more complicated in 2 or 3 dimensions, so let's just look at the one-dimensional case here. Now, how could we create this kind of standing wave? Well, let's say we have a tube that's filled with air, and on the left side we have a movable wall, so this can move back and forth, and on the right side we have a fixed wall, which can't move at all. So if you think about it, the right side of this tube is going to be a node for displacement because the molecules at the right end are going to be right up against this wall and they actually can't move back and forth because that wall is fixed. So we say this is a node for displacement. In other words, these molecules at this point are just not being displaced at all. On the other hand, if we look at the left end where we have a movable wall, these molecules are perfectly free to move back and forth. So that's what we would call an antinode for displacement at the left end. So you see what's going on here? We have a node for displacement at the right, an antinode for displacement at the left. So if we actually plot out displacement on this axis versus x position on this axis, we want to show that we have an antinode or maximum displacement here and then 0 displacement over here. And so this is what it looks like when that wall starts to move back and forth. Again, we have a standing wave with an antinode for displacement on the left and a node for displacement on the right. But also remember that when it comes to pressure, pressure and displacement are 90 degrees out of phase, meaning if displacement is at a maximum, then pressure should be at 0. So at the left side, we should have a node for delta P. So no change in pressure on the left side. And on the other hand, where displacement is going to 0 on the right side, where we have a node for displacement, we should have an antinode for pressure. So the pressure should be increasing and decreasing by a maximum amount at that end. All right, so this is what a one-dimensional standing sound wave actually looks like. And hopefully now you have some sense of how you can create a standing wave in a narrow tube like this. Again, if you have a movable wall on this side, that creates the disturbance that gets the air molecules oscillating. But if you have a fixed wall on this side, then the wave is confined to this space and you have a standing wave. If you want to take a look at the animation again, I left the link to the page where I got the animation from, so you can click that on the slides in the notes, and you can go to this page, check out all the information there if you want to. So the next thing I want to talk about is if we have a tube that's open at both ends, what kind of standing waves are going to be produced in this sort of tube? So consider a narrow tube with a length of L. It's filled with air, and it's open at both ends. So the first thing we should be thinking is, because the tube is open at both ends are going to be antinodes for displacement. In other words, these are positions where displacement is at a maximum because the air, again, is free to move. There's no wall at either of those 2 points. So what we have to do is consider what kind of standing waves can I get that have antinodes at this end and at this end? Well, the first thing I would think of is we could have an antinode over here and then half of a wavelength, which gives us another antinode over here. That would work as one of the possible standing waves. So in this case, the length of the tube is half the wavelength of our standing wave. That's one possibility. Now, another possibility is you have an antinode over here at the left side, and then you have a full wavelength, which brings you to another antinode on the right side. Now, in this case, the length of the tube is equal to lambda. L is equal to lambda, meaning you can fit a full wavelength inside of the tube here. Now, another possibility is that you have an antinode over here, then you have a full wavelength to get to this point, and then you undergo another half wavelength to get to the other end of the tube, and now you're at another antinode for displacement. Now in this case, you're fitting 3 halves of a wavelength inside of the length of the tube, so L is equal to 3 halves times lambda. And these are just the first 3 possibilities. You can just keep going with this and considering other types of standing waves that can fit in the tube. As long as you have an antinode at both sides, it works. So what's sort of the general formula we're seeing here? Well, in the first case, lambda is equal to 2 times L. In the second case, lambda is equal to just L. And in the third case, lambda is equal to 2 times L divided by 3. So the general pattern we're seeing is that the possible wavelengths are given by lambda is equal to 2 times L divided by n, where n is equal to 1, 2, 3, or any integer. So the first case we saw was n is equal to 1. That's where lambda is just equal to 2L divided by 1. The second case here is n is equal to 2, where lambda is equal to 2L divided by 2. So lambda is just equal to L in that case. And the third one we sketched out is n is equal to 3. So lambda is equal to 2L divided by 3. But again, you can keep going with this, and in general, the possible wavelengths are given by 2L divided by n. So we know what the possible wavelengths are. If we want to get the corresponding frequencies to say, what possible frequencies can we have resonating inside of this tube, then you would just use the fundamental relationship between speed v, wavelength lambda, and frequency f. So you can solve for f just by using this relationship here if you know lambda. Okay, so what happens then if we have a tube that's closed off at one end but open at the other end, like this? So we have a wall here that keeps the tube closed off at the right end, but it's open at the other end. Well, in that case, the closed end is going to be a node for displacement because air molecules are not free to move at this point. So they're going to have 0 displacement where the wall is. But the open end is going to be an antinode where we have a maximum displacement. So again, the game here is to kind of think about what types of standing waves can I have where I have an antinode at one end and a node at the other end. So the first example that I can think of is this. If we plot out the displacement on this axis versus x on this axis, we want maximum displacement at the left end, again, where we have the antinode. And then I want the displacement to go straight to 0, where I have the closed end, where we have a node. So this is what we're seeing here. Just go from the maximum displacement straight to 0, just like that. And that's a quarter of a wavelength. Okay, what I'm showing you there is a quarter of the overall wavelength. So L, the length of the tube, is equal to a quarter of the wavelength lambda. That's the first possibility. Now, the next possibility looks something like this. We have an antinode here where there's maximum displacement, and then we go half a wavelength to this point, and then a quarter of a wavelength takes us back down to 0 where there's no displacement. So that's 3/4 of a wavelength fitting inside of the tube. So the length of the tube is equal to 3/4 times lambda. That's the next possibility. And the next one after that is, okay, we have 0 displacement here. Now we undergo a full wavelength to get back down to that point, and then a quarter wavelength to get to 0 at the right end of the tube. So what I'm showing you there is 5/4 of a wavelength fitting inside of the tube. So L is equal to 5/4 times lambda in this case. And you can keep going with this, but it should be pretty clear what the general form is. In general, the possible wavelengths are given by lambda is equal to 4L divided by n, where n is an odd number this time. So n is equal to 1, 3, 5, 7, 9, only the odd numbers in this case. So if we look at the first example, that's where n is equal to 1. So if we solve for lambda, that says lambda is equal to 4L divided by 1. That's what the formula says. When we have n equals 1, we get lambda is equal to 4L. The second case, this is n is equal to 3 because lambda, if we solve for that, is 4L divided by 3. So again, our formula is 4L divided by n, which is equal to 3 in this case. And this third case over here is n is equal to 5, where again we have lambda is equal to 4L divided by 5. Now, as before, if we want the corresponding frequencies, we can just use v is equal to lambda f. Since we know what lambda is, we can solve for the frequency f using that relationship. So let's do an example. Let's look at standing waves in a tube. So a simple flute is made from a hollowed out tube, which is 25.5 centimeters long, and it's open at both ends. So what are the 4 lowest standing wave frequencies that can resonate in this tube in units of hertz? And what are the corresponding wavelengths in units of centimeters? We're going to take the speed of sound in the tube to be 343 meters per second. So let's work this out. Okay, so we'll start by remembering that for a tube that is open at both ends, the possible wavelengths are given by lambda n equals 2L divided by n, where n is equal to 1, 2, 3, or any other integer. And we'll also remember that there's a fundamental relationship between wavelength and frequency, which is v is equal to lambda times f. And we can rearrange that to say f is equal to v divided by lambda. So here's the strategy. We're going to directly calculate the wavelengths using this equation. Lambda n is 2L divided by n. And then we'll get the corresponding frequencies by taking v divided by lambda. Now, we want the lowest frequencies and that's f, by the way. And since f and lambda are inversely proportional to one another, we must be talking about the longest wavelengths. So what I have to do here is calculate the 4 longest possible wavelengths, and we'll do that again by using lambda n is equal to 2L divided by n. So the longest possible wavelength is when we plug in n equals 1, in which case lambda is equal to 2 times L, which is 25.5 centimeters, divided by 1, which comes out to 51.0 centimeters. Okay, if we want to do 2, 3, or 4, the only difference is on the bottom of that fraction. We're plugging in n equals 2. So lambda in that case would be 2 times 25.5 divided by 2, which is just 25.5 centimeters. If you plug in 3, you're going to get 17 centimeters. And if you plug in 4, you'll see that you get 12.8 centimeters. So these are the wavelengths for the first 4 values of n. So next, we'll calculate the corresponding frequencies, where f, again, is equal to v divided by lambda. For n equals 1, this gives us 343 meters per second for the speed, divided by 51 centimeters, or 0.510 meters for the wavelength, which comes out to 672.5 inverse seconds. Keep 3 sig figs on that, which is 673 hertz. So this is what we call the fundamental frequency, which is the lowest frequency. Okay, so the next values of f are for n equals 2, 3, and 4. And basically, we're just doing F is equal to V divided by lambda for the next three values of lambda that we calculated earlier. So I'll just tell you how these calculations come out. We've got F equals 1,350 hertz for n equals 2, 2,020 hertz for n equals 3, and then 2,690 hertz if you plug in n equals 4. So those are the lowest four frequencies that can resonate in the tube. That's how we do it. All right, so here's a conceptual question that I want you guys to think about. The speed of sound in air depends somewhat on the temperature. For instance, the speed of sound is 343 meters per second when the temperature is 20 degrees Celsius, and 331 meters per second when the temperature is 0 degrees Celsius, assuming atmospheric pressure. Will the standing wave frequencies in the flute from the previous problem be the same at 20 degrees Celsius and 0 degrees Celsius? In other words, are the frequencies going to stay the same even if the temperature changes? And if not, how can the instrument be modified to make sure the frequencies will stay the same as the temperature changes? So again, this is sort of a conceptual thing. Pause the video for a second, look over the equations that we've developed so far, and see if you can make use of them to answer this question. When you think you have an answer, come back to the video and we'll go through it together. Okay, so we'll start by writing down two equations. The first one is V is equal to lambda times F. And the second one is lambda is equal to 2L divided by N for N equals 1, 2, 3, and so on. This, of course, applies to standing waves in a tube open at both ends. Okay, so this question pertains to the frequencies, values of F, which are given by V divided by lambda, or V divided by 2L over N, which we can write as V divided by 2L times N. So here's the idea. At low temperatures, V decreases, right? So that will lower the frequency of your standing waves unless you change the length of the instrument, unless you change L. So you need to decrease L to keep F the same. And that means you're shortening the instrument. On the other hand, at higher temperatures, if it's a really hot day outside, V will increase. And again, if you just don't change the length of the instrument, if you keep L the same and you increase V, that's going to cause the frequencies to increase. So you better increase L to keep the frequencies the same, to keep F the same. And that means you're lengthening the instrument. So most wind instruments have some way of either shortening or lengthening the instrument to make these fine adjustments to keep frequencies the same, because of course sometimes the temperature changes and you're going to need to compensate for that. So this is how it works. So I'd like to introduce a topic that we'll go into a lot more depth on in the next video, but here I just want to introduce it to you. And this is interference of sound waves. So remember the superposition principle that we developed back in chapter 15. When two waves meet at the same position in space and at the same moment in time, you can simply add their displacements. So if we have two waves, let's call them d1 of x and t for the displacement of the first wave, and d2 of x and t for the displacement of the second wave, I simply add those two functions together to get the total displacement of both waves when they're together. So this leads us to the idea of constructive and destructive interference. Okay, these are two different ways that waves can add together. So for simplicity, let's imagine that we have two waves that have the same exact amplitude and the same exact frequency. So when they interfere constructively, this occurs when the waves are in phase, meaning the peak of one wave exactly lines up with the peak of another wave, and the trough of one wave exactly lines off with the trough of the other, so that when we add them together, let's think about what happens. When this one is at zero, this one is also at zero displacement, so the total is zero displacement at that point. But when this one is at a peak, this one is also at a peak, so I have to add those two peaks together to get an even bigger peak than before. When this one is at a trough, this one is also at a trough. I add those together to get an even bigger trough than before. So when the waves are in phase, we say they interfere constructively because the total wave has a bigger amplitude than what we have before. Okay, this gives us the largest possible total amplitude. On the other hand, if we have destructive interference, this occurs when the waves are 180 degrees out of phase, and effectively they cancel each other out. So now, when this one is at a peak, this one is at a trough. And when this one is at a trough, this one is at a peak, so they're 180 degrees out of phase with each other. And let's see what happens. Well, if I add this displacement, which is positive, to this negative displacement, I'm going to get zero. And then if I add this negative displacement here to this positive displacement here, again, I'm going to get zero. In fact, I'm going to get zero across the board. These two waves are effectively canceling each other out. So I want to just put this in your head that when two waves meet, they can interfere constructively, giving you a bigger wave than before, or destructively, where they effectively cancel each other out. And both of these are possible outcomes. And of course, it's going to be important for us to know under what conditions do we get constructive interference and under what conditions do we get destructive interference. And what matters here is the phase difference between the two waves. So here, when we talk about the phase of a wave given by phi, we're referring to the argument of the sine function. In other words, we're referring to what quantity is inside of the sine function. That's our phase phi. So the phase difference between two waves would just be delta phi, where we take phi 2 minus phi 1, and we'll take the absolute value of that just to ensure that it comes out positive. That's the phase difference between two waves. And this is what determines the amplitude of the resultant wave. Remember, if we have constructive interference, we get the biggest possible amplitude when we add the two waves together. Destructive interference, we get the smallest possible amplitude. So which one of those we're going to get depends on delta phi. Okay, so what's the condition that has to be met for constructive interference? Where again, we add the two amplitudes to get the total and we get the biggest possible total amplitude. Well, that would be delta phi equals 0, meaning they're exactly in phase. But if you think about it, 2 pi would also work because 2 pi is really the same as 0 because you go right back around to where you started. Or 4 pi, or really any even multiple of pi is going to work to make the waves completely in phase. So in general, what we can say is delta phi is equal to 2n times pi, where n can be 0, 1, 2, 3, or any integer. Okay, that's the condition that has to be met for constructive interference. On the other hand, for destructive interference, where you get the smallest possible amplitude when you add the two waves together, well, pi being 180 degrees or pi radians out of phase is going to work. But also 3 pi would work because, again, after 3 pi, you're right back to where you started. And then 5 pi would also work. Basically, any odd multiple of pi is going to work for destructive interference. So delta phi, the way we can write this is 2n plus 1 times pi, where n is equal to 0, 1, 2, 3, and so on. So let's just try this out. If you plug in 0, right, you're going to get 2 times 0 plus 1 times pi. So that would just be pi, the first result. If you plug in 1, you're going to have 2 times 1 plus 1, which is 3 times pi, so that's 3 pi. You plug in 2, you get 2 times 2 plus 1, which is 5 times pi, so that's 5 pi. Again, this is a general formula that works to give us destructive interference between two waves. So we're going to go a lot deeper into this topic in the next video. We'll end this one here. So I'll see you in the next one. Until then, take care. See you later.